Hello, everyone. Welcome back. So today we'll learn about antiderivatives and also begin to talk about integrals. So this is kind of the second half of what calculus is about. The first half is about derivatives and about the instantaneous rate of change of a function at a point. And so with antiderivatives or integrals, we're essentially, it's like an accumulation. We're taking those small changes and adding them up, and that gives us what's called an integral or an antiderivative. So that's what we begin learning about today. So our goals are to be able to find antiderivatives of common functions, learn how to do that, and see how it's related to derivatives, and also begin to learn about integral notation, the way it's written, and also find what's called indefinite integrals of common functions. So first, the antiderivative. And so antiderivative is kind of, in a way, it is kind of the way it sounds. So you know how to take a derivative, you know what that means. Well, the antiderivative is the opposite of that. So what it is, a function we're going to call a capital F. It's called the antiderivative of another function, small f, and I'm just using the same notation people often use, on some interval. If you take the derivative of big F, you get small f, then big F is what's called the antiderivative. So we're doing the derivative in reverse. What function gives you a derivative of small f? And that's going to be big F. Okay. This is once again, in other words, F is the antiderivative of F. If you're taking the derivative of F, big F gives you small f. This is define antiderivative is going to use the rules of differentiation backwards. And this next point mentions a constant, and I want to talk about that here in just a moment. So first, let's go over to the right and talk about some examples and kind of learn about, from the basics, learn how this works. So let's start with this function here. Let's start with number 1. Let's start with f of x is equal to 2x. Okay. Now, let's ask ourselves, what function has a derivative of 2x? Okay. In other words, what function, if I take the derivative of 2x, does it give me? If I take a function, takes a derivative, gives me 2x, what function am I starting with? Okay, so think about that for a second. And I think you probably guess that your f of x, one example, is going to be just x squared. Okay, now if I want to check, let's do f prime of x. And we know if we take the derivative of that, x squared is 2x. That checks. Okay, that's what this says. So capital F prime of x is equal to f of x. Okay, but this isn't the only derivative, not the only antiderivative. So this is an antiderivative, but not the only one. Okay, I'll explain what I mean. All right. Well, what if I have, let's also call this f of x, capital F of x. What if I had x squared plus 1? Okay. If I take the derivative of that, obviously that's also 2x. Okay. Or what if I do, or capital F of x is equal to x squared minus 3? Okay. And so if I take the derivative of that as well, of course, that's also 2x. Okay. So basically, what this means, or what this tells us, is that as long as there's some constant here, since the derivative of a constant is 0, as long as there's attached some constant to it, it can be x squared plus any constant. Okay. So in general, f of x is equal to x squared plus, and we call it c, capital C, as we often call it, where c is any constant, and the constant could also be 0. Okay, as it was in the first example. So we had 3 examples here. Okay, if f of x is simply x squared, it gives me a derivative of 2x. X squared plus 1 gives me a derivative of 2x. X squared minus 3 gives me a derivative of 2x. So plus or minus any constant here, the c, I'm doing plus, but it could also be c, could be negative. Give me any constant, I'll still get a derivative of 2x. So all these are what are called antiderivatives. This is what this next point over here. It says the family of antiderivatives of f is f plus c, where c can be any constant, including 0. Once again, that's true because take the derivative of any constant, that's 0. So there's a whole family of these. Okay, now graphically what that means, let's think about that. Let's go to Desmos for a minute. Let's just graphic, or it's just x squared, y equals x squared. Of course, we know that's a parabola. Now, also nice thing you can do with Desmos is actually add plus c. Okay, and it says, it says add slider for c. What that means then, remember, think about graphing. This c is just going to take this graph and move it up and down. Okay, so if c is 0, it's a regular parabola with a vertex at the origin. If c is a positive number, it's going to take that shape to simply move it up. Keep the same shape, just move it up. If it's negative, it moves it down, but it keeps exactly the same shape. Let's go back to 0 for C0. Okay, now let's say at a place like 2. So let's do x equals 2. Okay, I'm just drawing a horizontal line at 2 just to make a point. Let's actually zoom out just a bit. What this means, if you notice the slope of the tangent line at 2, you can imagine what the slope of the tangent line looks like, or what the tangent line would look like. Okay, now if I change c, if I move this graph up and down, notice the slope of the tangent line at 2 doesn't change. Okay, no matter where I move it, and that's the idea. So basically, I can add any constant to my function, and we'll have the same slope. The slope of the tangent line will be the same at the same x value everywhere. Okay, so basically when you do this antiderivative, it can vary by constant. Now later on in our video, we'll talk about how to, if you actually have a value of a function, we actually find out what that constant is. But right now we just have this generic constant. That's part of the antiderivative. Okay, so let's practice with a few more examples of this. Number 2, let's say f of x is equal to -3. Okay, then what function would give us an antiderivative of that? What function would give us a derivative of 3? Well, if you just have a constant, that means it's basically going to be your f of x is going to be -3x. Okay, because if you took the derivative of this, you get -3. And of course, once again, this plus c. Okay, now let's think about this one a little bit more. Takes a little more thought. What if we just had this time, instead of 2x, what we had before, what if we have just simply x squared? I'm sorry, not x squared, just simply just x. Now, if we compare this to the other one, the first one we started with, that was a 2x. We had a 2 out front. This time we don't have the 2 out front, we just have an x. So if we think about what this has to be, well, we know to get an x the first power, we have to have an x to the second power to give us that. But somehow we need to get rid of the 2, okay? If you take the derivative of this, let's go ahead and think about this. So f prime of x is going to be the derivative of 2x, but there's no 2 here. So we have to divide this. We actually have to divide this by 2 to make this work. So somehow the 2 has to go away. The way to make that happen is that we have 2 down here. So the 2's will cancel out. We just, also don't forget we have the plus c. And so, oh, sorry, this f prime of, oops, c in the wrong place. Okay. So plus c here, because then we take the derivative of that, we just get x. Okay. Now let's introduce one more idea. Our next idea. That's something called the indefinite integral. And that's just basically all we're doing here is a different notation, different way of writing it. So we're doing the same thing as antiderivative, we're just writing it a different way. And this is something called the indefinite integral. So basically doing the opposite of taking a derivative, it's antiderivative, as you'll see, is going to be called integration, taking an integral of something. And that's what this Kirby sign means. And whenever you see that, that means you're doing an antiderivative. You're going backwards from a derivative. Okay, so for now, we're just doing that. And later on, in other videos, and continue this, learn about the integration, we'll learn about kind of what this means, where this notation comes from, and also why we have this differential d of x here, why that's there. And basically, this just means doing the same as an antiderivative. Okay. Once again, this is called an integral of f, where dx is a differential of x. And once again, c is what's called the constant of integration. So anytime we do this antiderivative, the constant of integration. And this then is called, because we have the c, it's called an indefinite integral. There's something called a definite integral, which we'll learn about in the future, but not today. But that basically allows us to essentially find out what the c is. And once again, say at the very end, the indefinite integral of f is the same as the antiderivative of f. Okay. So let's actually practice with something else. Let's go back over here to the right. Okay. So an indefinite integral is the same as the antiderivative. It's just a new name and kind of a new symbol. All right. So, for example, what I just did, if you see this integral symbol, this kind of curved, looks a little bit like a really stretched out S, x times dx, this is exactly the same thing we just did, okay, is the antiderivative of x. And that's just going to be, as we just saw, x squared over 2 plus c. And once again, for everyone sure, just take the derivative and check. Okay, that's the new notation. All right. So what we're going to do then is practice with a few of these. I'm going to see a few more examples, both derivatives, antiderivatives, and indefinite integrals. And we'll see how these work. Now, actually, before we do that, let's also go and introduce our next rule. Let's do something called the power rule. It's called the power rule for definite integrals. Okay. What the power rule says is if you have something just like this, okay, back what we just did was the power rule for definite integrals, then basically you have x to the p, where p is your power, okay, dx. And what you do is, remember, when you take the derivative, if you have x to the p and take the derivative, then what we do is reduce the power, new power by 1. Here we're doing the opposite, okay? We have to increase the power by 1, but also, if we have no constant out front, we have to put that p plus 1, that new power, down below as well, then plus c. So let's practice with this. Let's do some examples. So number 1, so the indefinite integral of, let's do x cubed dx. Or no, just x squared dx. We'll get to cubed possibly later. X squared dx. Okay? So we're going to use this power rule. What it says, we're going to have a fraction. Also have a plus c. Let's go for the plus c there. Okay, so just like, once again, if we're undoing a derivative, in a derivative, we reduce the power by 1. So here, we have to increase the power by 1. So there's going to be x cubed. And basically, we have to put this new power here. So actually, let me do it the same way here. So this is going to be 2 plus 1, our new power. We're adding 1. For the derivative, we subtract 1. And doing the opposite of that, we add 1. And then we have 2 plus 1 down here. And of course, that's just going to be x cubed over 3 plus c. Okay, so now let's check this. Okay, so take the derivative. Okay, let's take the derivative of this. So our constant out front is 1/3. Okay, and the derivative of x cubed is 3x squared. Then plus the derivative of the constant is 0. And of course, here's the 3's cancel out, and we're left with x squared. That checks. Okay, so that's what's called the antiderivative, or the indefinite integral of x squared. Okay, is this x cubed over 3. Okay. Let's practice with, let's do a few more with the power rule. Okay, what if we had the indefinite integral of, say, x to the fifth dx? All right, so same rule. We get the plus c. Okay, we have x. We're going to increase the power by 1, which is 6. 5 plus 1 is 6. Then put that new power down here, x plus 1. So x to the 6 over 6 plus c. Once we take the derivative of that, you'll see that's true. Now, this rule says, notice this rule says that as long as p is not equal to -1. Let's actually do a couple with a negative powers. So 3, let's say we have 1 over x squared dx, which is the same as x to the -2 dx. Okay. Now, same rule. This one may want to write it out a bit more. Okay, so go ahead and put the plus c. So remember here, we're adding the powers. It'll be -2, -2 plus 1. And down here, -2 plus 1. Okay, and of course, then that's going to be x to the -1 over -1 plus c. And we can clean that up a bit. And you can write that as negative and then 1 over x plus c. Okay, that's its antiderivative. Okay, now this rule also works if you have unusual powers. Let's say we had x to the, let's do a decimal, 7.3. Okay, works exactly the same way. This rule works as long as p is not equal to -1. Okay, so same thing, plus c. So we add 1 to our power, so x to the 7.3 plus 1. And then down here, same thing, 7.3 plus 1. And so this would be x to the 8.3 over 8.3 plus c. And of course, you can also kind of clean it up a bit. And if you do, this is 1 over 8.3 times x to the 8.3 plus c. If you divide that, 1 by 8.3 is probably be another decimal, so I might have to approximate it, but let's see what the calculator says. 1 divided by 8.3. Yeah, so this can be approximate because I have to round it off. It's going to be about 0.12 x to the 8.3 plus c. Okay. Now, if you notice, let's also talk about some things that are not powers. Okay, so hopefully you got the idea of the power rule. Let's talk about some things that are not powers. Well, what if you have something like, let's talk about the case where it is 1 over x. Okay, so this can't be x to the first. What is 1 over x dx? Which also, if you write that as a negative power, is the same as x to the -1 dx. Okay, this one here, power rule doesn't work. Because if you notice, if you tried it, your new exponent would be x to the 0, which would make this whole thing 1. It wouldn't even be in the variable anymore, so that doesn't make any sense. Okay, let's think about what function has a derivative of 1 over x. Okay, so think back, what function has a derivative of 1 over x? So if you remember, that's actually natural log. So this would actually be, so the derivative of 1 over x dx, that's why you don't use the power rule here, it doesn't work. But this is something else. This is going to be actually the natural log of x, once again, still, plus c. If you want to check it, check it. That's going to give you the same thing. Okay, now let's talk about a couple more rules we'll use. And these rules should be familiar. These are based the same sort of rules you see with derivatives. Okay, so it's called the constant multiplier rule and the sum of difference rule. We're on the left. So basically, just like a derivative, if you have a constant, you take a derivative, you have a constant in front, you essentially kind of move the constant out front. You do the same thing with the indefinite integral. Okay, so move the constant out front. And if you have a sum or difference, and that's why I have a plus or minus here, plus over minus just means plus or minus, then basically, just like a derivative, you have a plus or minus of a sum or difference. You take the derivative of each part, you do the same thing with the integral. Just make sure, especially with subtracting, you use the correct order. And it says these are rules the same for derivatives. And also, there are other derivative rules. A lot of times, there's software often that can do this for you, but also if you just look at integral tables, search for integral tables on the web, you also find integral for unusual integrals. People have done a long time ago, especially for calculators and computers. When they need an integral, sometimes people took the time to actually find these integrals. So you can search that. But we may not look at that right now. So let's do a couple, practice a bit with these rules. Okay, so let's say I can do the same one we've already done. So the integral, an indefinite integral of 2x dx. Okay, we already know this was x squared. But if you didn't know that, you could just simply bring the constant out front. And so this constant rule says 2 times the integral of x over dx. This gives us a little practice, a little more practice with the power rule. Okay, now this then is going to be 2, and then from our power rule, to make it all three there on the same screen. Yeah. So just x, the derivative, the antiderivative or the indefinite integral of that is going to be x squared. This is x to the first, make it x squared over 2 plus c. And of course, the 2's cancel out. And that's just going to be x squared plus c. Okay. All right. Let's combine this idea with a couple more. Let's do one or two more like this. So number 7, let's say we have the definite integral of 3 e to the x dx. Okay. So this, we haven't done the integral of this one yet. That's okay. So once again, the constant moves out front. And so it's going to be 3 times the integral of e to the x dx. And remember, what is the integral, or what the question you want to ask is, you take the derivative of what function just gives you e to the x. And remember, exponents are their own derivatives. And so this is actually going to be first 3. Don't forget about the 3. Then the antiderivative of e to the x is just e to the x. And then, of course, don't forget plus c. Okay. Let's do a quick example with another example with the sum and difference rule. Okay. Let's say we have the integral or antiderivative of the sum. Let's say x squared plus x to the 5th dx. Of course, remember, we can't combine those, they aren't like terms. And so from our rule, we have the, it's like distributing. So the integral of x squared dx, and don't forget to put the dx as well, plus the derivative of the antiderivative x to the 5th dx. Okay, and we'll use the power rule in both of these. Now, our power rule says that if x squared is going to be raise the power by 1, x cubed, and then put the new power down here, plus c. And then for the second part, x to the 5th is going to be x to the 6th over 6 plus, let's call it d, where d is also, so c and d are constants. Okay, or actually, let me call them something different. Let me just make this different here. Call them C1 and C2. Okay, where C1, C2 are both constants. Now, why did I do that? Well, what I can do then, I can write it like this. X cubed over 3 plus x to the 6 over 6 plus C1 plus C2. So all I'm doing is changing the order. I can do that. Okay. And now I'm going to write this. I'm going to call this just equal to C. So C1 plus C2 is equal to C. Once again, C is just another constant. So if I add two constants or subtract two constants, it's still just a constant. So I can basically combine both those constants into one. Okay. And so finally, this is going to write as x cubed over 3 plus x to the 6 over 6 plus just c. Okay. Actually, give me a moment. I need to make sure I have enough room for my next few examples. Okay. Let's do number 9. Let's do one more kind of like this. Okay. Let's do one that may be a little bit more challenging in the sense that it might be clear at first what the antiderivatives are. So cosine of x. So we're doing this time a difference. So make it a difference. So here, of course, being a difference, the order is important. Cosine of x minus 1 over 1 plus x squared, and this is all to the dx. Okay? The cosine of x minus 1 over 1 plus x squared dx. Now, once again, I can break this up into 2. The integral of cosine of x dx, don't forget the dx, now minus the integral of 1 over 1 plus x squared dx. Okay. Now, these you might have to think about just a bit. Okay. In fact, let's do something different. This time, let's go ahead and put our c out here. Okay. So we could do the same thing we did in the previous example. You write two different constants, but we can always combine them into one. Okay, constant for each one. So go ahead and put just one constant out here. Now, once again, think about this. What function gives me a derivative of cosine of x? You might have to think back or maybe look back your notes, but that's going to be sine of x. Okay. So sine of x, if you take the derivative of sine of x, you get cosine of x. Now, this one's probably a bit harder. This one you may not remember that well. I was going to look back your notes, look back in your book, or even look it up, but this is actually the inverse tangent. Okay, so 1 over 1 plus x squared is the inverse tangent, so this is the inverse tangent of x. Okay, then plus c. All right, and so that is think of as either the indefinite integral or the antiderivative. Okay, now let's do one more concept, one more thing I want to do. And that's something called a particular antiderivative. And what this means is that if we know, well, I'll write this out. Basically, it says if we know you have a function input and output, the antiderivative function, such as like f of a equals b, we can actually find the value of our constant c. Okay, so we go back to Desmos, where our picture was. Okay, we said here, he said if I change c, all these have the same derivative at like any point, and here are highlighted specifically x equals 2 at any point. Now, if I actually know a function value, okay, so for example, like here, if c is 0, then at this point here at the origin, if x is 0, y is 0. If I know that to begin with, then that actually tells me what my c is going to be, okay? So the only value that will give me the same derivative here at 2, and will have this point here on the function, that's only one of those possible parabolas. And so that fixes it, that tells me exactly which one it is. So I can actually find out the value of the constant if I know a point on the graph. Okay, if I know an input and output or a point on the graph. Okay. So let's do an example of that. Okay. So here basically I'll say find C using input and output. Or once again, think as a point on the graph. So number one, let's say we have this. Our function f of y is equal to 3y cubed plus 5 over y. And here I have f of 1 is equal to 3. And also want to specify this is for being y greater than 0. We'll see why here in a minute. Okay. Now, so if you remember the way our notation is working here, once again, kind of using the same style people used before, small f, basically small f is the derivative of big F. So if I take the derivative of my function, that's going to be my antiderivative. If I take the derivative of that, that's going to give me small f. Okay. Now, let's actually do a couple things here. So the way this is written right now wouldn't be the easiest way to try and find this antiderivative or indefinite integral from this. Okay, so let's actually work with this just a bit. Let's split this up into two fractions to actually make this simpler. So 3y cubed over y plus 5 over y. Of course, here we can cancel out some of the y's, cancel out one of them, make that a 2, and this is going to be 3y squared plus 5 over y. Okay, and so that's my f of y. Okay, so what I want to do now then is you can think this either using the notation you want the antiderivative or the integral notation. I'll just do the integral notation. So f of y is going to be this integral of 3y squared. Oops, don't need that parenthesis there. Plus 5 over y. This time, instead of dx, using a y as a variable, we call that dy. Okay. Now, just as we did before, let's break this up into 2. And so the integral of 3y squared dy plus the integral of 5 over y dy. Okay. And then find the antiderivative. Well, a couple more things. Let's actually pull this 3 out front. It's a constant, so we have 3 out front. The integral of y squared dy. And then here, I think this is also constant, this 5. Pull the 5 out front, and this is the integral of 1 over y dy. Okay? And so we're almost there. So now our function f of y is going to be, actually, hang on, I may need to just a little more, make sure I have enough space. I have one more example after this one. Yeah, that's enough. Okay, so we have 3, and then using our rule, this the antiderivative of y squared is going to be y cubed over 3. Also, we're going to put our constant out here. Think of two constants, we always combine them into 1. Plus 5. Now, once again, what's the antiderivative of 1 over y? We saw a minute ago that was the natural log of y. And here, the 3's cancel out, and we're left with, for our function f of y, is y cubed plus 5 times the natural log of y plus c. Okay. Now, so what we're going to do then is we want to actually find c. We're going to use the input value we had, which was that f of 1 is equal to 3. Okay. So this is similar to what you've probably done in algebra when you're trying to find the equation of a line. You're trying to find like the y-intercept b, you plug in a point and find b, kind of a very similar thing. Okay. So in this case, we're using y instead of x. By plugging in 1 for y, f of y, f of 1 is equal to 3. That's equal to just place the y's with 1's, 1 cubed plus 5 times the natural log of 1, and put parentheses around that, plus c, okay, and that's equal to 3. So, of course, 1 cubed is 1. Remember, the natural log of 1 is 0. So this whole term just goes away. And so what we have then is 3 equals 1 plus c. You get c by itself, solve for c. And then that's going to be that c is equal to 2. Okay, so f of y is equal to y cubed plus 5 times the natural log of y plus 2. Okay, and once again, this is what's called a particular antiderivative. That's what I called it anyway. A particular antiderivative. What just happened? Okay. Hmm. Or what I wrote just disappeared. Oh, I'm going to write it again, I guess. This is a particular antiderivative. And once again, the idea here is I had my function antiderivative, also had my function input output or a point on the graph, and that actually gave me the specific graph we're talking about. Now, if I change this, if I change this to a different values, like f of 5 is equal to 2 or something like that, then that would give me a different and particular antiderivative. This is one. And also, it's a good thing to try on your own. Take the derivative of this and make sure you get the antiderivative we had right up here. Make sure you get that. All right. One more example. So let's start right here. This should be number 2. All right, this has to do with acceleration and gravity. So let's say acceleration and velocity, rather. So acceleration velocity and position. I hope you remember, if think about position in terms of a variable for a variable time, you take the derivative of position, you get your velocity. Okay, position with respect to time is velocity, and then velocity with respect to time is acceleration. So now we're going backwards. Okay, so now we have to do this indefinite integral or take the antiderivative to go from acceleration to velocity to position. All right, so here's what we have. Our acceleration, a of t, is just a constant, which is 4. And v of 0, when t is 0, is equal to negative 3. And then s, for position of 0, is equal to 2. And these are both called initial conditions. Initial condition means those are conditions, you hear this in science a lot, in engineering a lot. Respect to time, so initial means beginning. So these are beginning conditions when time is equal to 0. What we're starting with a position of 2 and a velocity of negative 3. Okay? Now, so first, let's find velocity. And to do that, we're going to integrate acceleration. Handwriting on saying some of this isn't the best. Okay, integrate our acceleration. Okay. So the velocity is a function of time, is going to be the integral of our acceleration as a function of time. This time also we also have a differential. This time our variable is t, so it's going to be dt. Okay. Now, our acceleration is constant, 4. Okay. And we know if we have just a constant, that antiderivative is going to be just 4 times t. Okay, so the variable is t, then it's going to be 4 times t. So 4 times t plus, let me just call it c1. Okay, we have a constant here called c1. Okay, so 4t. That's our velocity. Okay, so now next thing I want to do before I move on is find c1. Okay, so do the same thing just did a minute ago. So we have as a value. Okay, so we're going to use the value we were given, which was that v of 0, our initial condition, v of 0 is equal to negative 3. Remember, the negative here for velocity has to do with direction. All right, and so what we're going to do is plug these in for this. And so this is equal to negative 3 and 4 at time 0. So 4 times 0 plus c1. Okay, and of course this goes away. So negative 3 is equal to c1. So in this case, our function of our velocity is going to be 4t minus 3. Okay, that's our velocity. What we did is we defined the velocity, we integrated acceleration, took this indefinite integral of that. Okay, we got our antiderivative, our indefinite integral, and then we use the initial condition, that particular condition, to find a particular antiderivative. Okay, in this case of that. Now we want to find position. So I apologize, sometimes I have trouble writing with these things. Find position And so to do that, we're going to integrate, let's abbreviate that, integrate velocity. Yeah, excuse me. Okay, so position, recall S of t is going to be the integral of v of t, and once again, with our differential dt. And now we're going to plug in this. Okay, so the integral of 4t minus 3 dt. And now we know how to do that. We practice with that, use our rules. We can break this up into two integrals. Integral of 4t dt minus, and once again, be careful that the order is important. This is a minus. The integral of 3 minus the integral of 3 dt. Okay, now constant here can come out front, and so it's going to be 4 times the integral of t dt minus 3 integral of 3 dt. Okay, so now let's integrate both. And once again, also I'm going to write my constant out here, plus c. Let's call it c2 this time, so I use c1. Okay, now 4 times that. Now if we use our rule again, the antiderivative of t is going to be t squared over 2 minus, and this is going to be 3 like we saw here. This was 4t before. This is going to be 3t, then finally plus c2. Okay, now here we can simplify some. This is going to 2 goes into 4 twice, so this is going to become 2t squared minus 3t plus c2, and that's my function for position. Okay, and then just like I did before, I want to find c2. I'm going to use the value I was given for my position function. S of 0, initial addition, S of 0 is equal to 2. So plug that in. So this whole thing is equal to 2. Then replace the t with 0. So 2 times 0 squared minus 3 times 0 plus c2. And of course, these are 0, go away. And so c2 is just equal to 2. So finally, after all that, function for my position is going to be 2t squared minus 3t plus 2. Okay. Now, this is also be good practice doing your own. Take the derivative of this once, get velocity. Make sure you get the same thing that you got before, 4t minus 3. Take the derivative again, have that, and then make sure you get the acceleration, which should be just 4. So, what we learned today. So, let's kind of summarize a bit for you. So, you learned about the basic idea of antiderivatives. That's where that went. So the antiderivative is kind of like it sounds like. It's the opposite or the undoing or the anti of going in reverse of a derivative. Okay, so it's asking what function gives you the derivative you have. And as we saw also, when we do that, an antiderivative, because the derivative of any constant is 0, we get what's called a family of antiderivatives, so a plus c. Okay, then we learned about a definite integral is the same idea as an antiderivative, just using a new notation. And then we learned some rules, the power rule, and also constant and sum of difference rules, and also how to find antiderivatives from other kind of functions. And we found if we know a function input and output, a point on the graph, we can actually find a particular antiderivative and actually find out what the value of c is. Thank you. Have a good day.